A system is defined as a quantity of matter or a region in space chosen for study. The mass or region outside the system is called the surroundings, and the real or imaginary surface that separates a system from its surroundings is called the boundary. The boundary of a system can be fixed or movable. Systems may be considered to be closed or open, depending on whether a fixed mass or a fixed volume in space is chosen for study. A closed system, also known as a control mass or just the system, consists of a fixed amount of mass and no mass can cross its boundary. That is, no mass can enter or leave a closed system. But energy in the form of heat or work can cross the boundary, and the volume of a closed system does not have to be fixed. If, as a special case, even energy is not allowed to cross the boundary, that system is called an isolated system. An open system, or a control volume, as it is often called, is a properly selected region in space. It usually encloses a device that involves mass flow such as a compressor, turbine or nozzle. Flow through these devices is best studied by selecting the region within the device as the control volume. Both mass and energy can cross the boundary of a control volume. So let's analyze this situation. A closed lid bottle of Dr. Pepper is placed in a refrigerator that is at 3 degrees centigrade. Should the bottle be treated as a closed system or an open system? How about when the lid is open? You will notice that in both instances, the system is considered as closed because mass did not cross the boundary in both instances. Any characteristic of a system is called a property. Some familiar properties are pressure, temperature, volume, and mass. Properties are considered to be either intensive or extensive. Intensive properties are those that are independent of the mass of a system, such as temperature, pressure, and density. Extensive properties are those whose values depend on the size or extent of the system. Total mass, total volume, and total momentum are some examples of extensive properties. An easy way to determine whether a property is intensive or extensive is to divide the system into two equal parts with an imaginary partition, and then each part will have the same value of intensive properties as the original system, but half the value of extensive properties. Extensive properties per unit mass are called specific properties. Some specific properties are specific volume and specific total energy. Matter is made up of atoms that are widely spaced in the gas phase. However, it is very convenient in thermodynamics to disregard the atomic nature of a substance and view it as a continuous homogeneous matter with no holes, which is called as a continuum. Density is defined as mass per unit volume, which is depicted here as m mass divided by v volume, and the units for density rho is denoted in kilograms per meter cubed. The reciprocal of density is called the specific volume, depicted by simple V, which is defined as volume per unit mass, that is capital V divided by simple m, which is also equal to 1 over rho. Sometimes the density of a substance is given relative to the density of a well-known substance. Then it is called specific gravity or relative density, and is defined as the ratio of the density of a substance to the density of some standard substance at a specified temperature, and usually this is given as water at 4 degrees centigrade, for which rho H2O is equal to 1000 kilograms per cubic meter. So in this case, specific gravity would be equal to the density of the substance rho divided by rho H2O, which is the density of water. Now take a moment to pause this slide and work on this problem. Now let's look at state and equilibrium. Consider a system not undergoing any change. At this point, all the properties can be measured or calculated throughout the entire system, which gives us a set of properties that completely describes the condition or the state of the system. At a given state, all the properties of a system have fixed values. If the value of even one property changes, the state will change to a different one. Thermodynamics deals with equilibrium states. The word equilibrium implies a state of balance. In an equilibrium state, there are no unbalanced potentials or driving forces within the system. A system in equilibrium experiences no changes when it is isolated from its surroundings. There are many types of equilibrium, and a system is not in thermodynamic equilibrium unless the conditions of all the relevant types of equilibrium are satisfied. For example, a system is in thermal equilibrium if the temperature is the same throughout the entire system, that is, the system involves no temperature differential, which is the driving force for heat flow. Mechanical equilibrium is related to pressure, and a system is in mechanical equilibrium if there is no change in pressure at any point of the system with time. If a system involves two phases, it is in phase equilibrium, when the mass of each phase reaches an equilibrium level and stays there. Finally, a system is in chemical equilibrium if its chemical composition does not change with time. That is, no chemical reactions occur. A system will not be in equilibrium unless all the relevant equilibrium criteria are satisfied. Let's look at the state postulate. As noted before, the state of a system is described by its properties. But we know from experience that we do not have to specify all the properties in order to fix a state. Once a sufficient number of properties are specified, the rest of the properties assume certain values automatically. That is, specifying a certain number of properties is sufficient to fix a state. The number of properties required to fix the state of a system is given by the state postulate. So the state postulate is depicted as follows. A state of a simple compressible system is completely specified by two independent intensive properties. A system is called a simple compressible system in the absence of electrical, magnetic, gravitational, motion, and surface tension effects. These effects are due to external force fields and are negligible for most engineering problems. The state postulates requires that the two properties specified be independent to fix the state. Two properties are independent if one property can be varied while the other one is held constant. For example, temperature and specific volume are always independent properties, and together they can fix the state of a simple compressible system.